Hi everybody. I'm PhD student in statistics, working in France, under the supervision of Thierry Klein and Xavier Gendre, and I'm going to talk about geometry. So first, as an introduction, I'd like to remind you that geometry is already used in aviation, right? When you design airfoil or when you design a new procedure. And statistics has also been playing a huge part in this community, playing a key role for traffic forecast where you are going to use time series, right? Or predictive maintenance where you can borrow from survival analysis. But the statistical analysis of aircraft trajectories has been underexploited in the ATM literature. And I think there is one reason for this, is that the usual statistical toolbox is not enough, right? Multivariate statistics suffers from the very high correlation in time that you have between two consecutive points in a trajectory. And even if you achieve to take this into account, you have the so-called curse of dimensionality when you have too many variables for too few individuals, right? So, okay, why not using other topics in statistics? Time series, for instance. But problem is you have irregular sampling with ADS-B data, and you have different durations. So it's a big challenge, right? On its part, I think that there is a current institutional context where you have greater availability of trajectory data with the R&D data archive provided by Eurocontrol. It gives you access to more than 17 million of flights as of April 2022. And of course, the Open Sky network has grown now to a very big amount of receivers all around the world. And there is a need for statistics, right? In past Open Sky synopsia, we have seen that many methods are relying on statistics, trajectory generation or pattern identification. And here, I'd like to introduce you to what is up to date in statistics, that is to say, geometry. Indeed, there are many papers now in statistics that try to make the most of differential geometry. Basically, it's a topic in geometry where you study complex shapes or spaces, but you can see them as locally flat, right? And in this world, parametric curves, they are super useful to describe a trajectory because it takes into account many problems we have said already. And it's also a good framework to study the shape of things, right? So this is the question I'm going to focus on. I'd like to show you how geometry can provide the right framework to study shape differences between the two data we have, right? The Eurocontrol version of a trajectory and its ADS-B version. The scope is flights going from Toulouse to Paris in 2019, but it can be extended, of course. Even with some visual things, you can be sure that ADS-B is very interesting. When you look at linear interpolation, focusing on Paris-Orly airport, you see many shape differences, right? And you want to take this into account and to compare how far are the two trajectories. In this presentation, I'm going to develop three aspects. Quantification, so we want to compute kind of the shortest path between the two versions of the trajectory, but also to provide visualization, because we also have other distances, Hausdorff distance, etc., but you're not able to compute and to visualize properly the geodesics. And then I'm going to show you that the distance we are going to build together, it can be used in practice now in usual problems, such as clustering. So what is the shape of a trajectory? This refers to a field, shape analysis, that was developed by Kendall and colleagues, for instance, Dryden and Mardia, and it's all assume that we now define shape as follows. It is all the geometrical information that remains when location, scale, and rotational effects are removed from an object. Let me show you a very simple example you all know about, triangles. There are several shapes of triangles, right? And if we focus on the first class, the right triangle on the left-hand side of the plot, you see here that you want to say all these triangles have the same shape, even if they are rotated to one another or scaled or whatever. You really want to cluster triangle shapes, removing these kind of effects. So what can we do in practice? In the past, shape analysis is done identifying a set of landmarks, right? So we denote by K the number of landmark, and N is the dimension we are living in. For triangle, sorry, up, no, why is it going? Okay, like it's, thanks. So there is an MQC at the end, so do you really want to rush? Here, obvious landmark is angles, right? And the space we live in is R2. You have these order points, right, the landmarks, and you can build the so-called configuration matrix. Basically, you just store the landmark in a matrix, very simple, and you study the shape of the set of configuration, L and K. It is the one of n times K matrices, and you exclude strange cases where all the landmarks are located at the same place, right? So in the past, very simple example of landmark shape analysis, studying the shape of moose vertebra. So you locate landmark, you have scientific biologists that say, okay, these are the specific points you need to look at to study this shape. And then you have your landmark and you basically perform all the thing you know in shape analysis. So what is shape at the end? You have many configurations, right, for the triangles. And if you remove everything, like the three effects we were talking about, translation, scale, and rotation, you build equivalent classes, right? So basically in geometry, to take some effects into account, you use group theory. So I'm not going to speak about it too much, but basically there are three effects of interest here: the translation group, scaling group, rotation group. We want to cancel these effects. To study trajectories, it's not straightforward to find landmarks. Why? Because first, the choice of landmarks is very subjective, right? So if I ask you where should I put my landmark on a given trajectory, you may use 3 landmarks, 4, you may rely on flight phases or not. It really depends on you. There is no, in ADSB data, for example, no pilot saying this is the right place for the landmark, right? So no scientific landmark. So as a statistician, okay, I might use derivatives or things like this. But the problem with these mathematical landmarks is that they are going to be very imprecise with Eurocontrol data because the sampling is sparse, right? So you are going to misestimate the derivatives and stuff. So you're not departing on the same line with ADSB data. Lucky for us, there is a new framework that was developed by Srivastava and co-authors, and they proposed a very convenient way to describe shape of curves in Rn. And if you see a trajectory as a curve, it's very easy to model the shape and to do some relevant analysis. So, okay, trajectories, we can see them as parameterized curves in R3. So if you do so, you depart from time interval, and then you end up in a 3D space, right? Very easy. And to capture the shape now, we are going to use the so-called square root velocity function instead of landmark. So you say, okay, I'm not describing shape of a trajectory with matrices. I'm going to use another curve that is called the square root velocity function. Don't be afraid. It's very friendly expression. I just want you to notice that we basically use the derivative. Like derivative captures a lot about shapes, right? You know it from the analysis class you may have taken in the past. If you want to do optimization or to look at variation, you look at derivatives. Okay, we do the same thing here. It's like of a normalized derivative, if you wish. Okay, and what is very cool is that when you have this kind of square root velocity function, you can associate it uniquely to the curve to the trajectory you are studying. And it naturally removes translations. Remember derivatives, they don't take into account constant, right? So cool. Square root velocity function naturally remove translation effects, which are kind of a noise parameter for us in shape analysis, right? Scale effects, very easy. As data scientists, we rescale everything to be unit length, and then you have removed two effects. Third one is rotation. So this one is a bit trickier, okay? We need to fully do the optimization problem. And fourth one, parameterization, is a bit new here. With landmark, you are not taking into account time passing through the shape you are looking at. But now you introducing with this new framework a speed at which you travel along the curve, right? So you need to take into account that maybe speed can change. The shape can be the same, right? But the speed can change, and you don't want this to be part of the shape analysis thing. So once you take these four effects into account, well, the distance between two shapes is the shortest one once we have removed rotation and reparametrization effects. Okay, and lucky for us, with the square root velocity function, the computation of geodesic is very easy because we are on a sphere. And coming from aviation, you know that geodesic is very easy to compute on a sphere, right? So it's a bit more complicated here, but basically that was the main idea. So in practice, enough of theory. I took flights departing from Toulouse-Blagnac and landing at Paris-Orly. I departed from the Eurocontrol database using all the information I had, the actual field flight plans, and then I tried to match the trajectories with ADSB data using the aircraft database from OpenSky Network because, of course, one is relying on ICAO 24 and the other one on registration numbers. So you have a bit of work to do here. But basically now we are able to compute the distances between the two versions, right? And what is very interesting is that you have some trajectories for which you're not very far from the Eurocontrol version when you look at the ADSB. Why? Because it doesn't mean you are following the flight plan exactly. It means that if you bend the Eurocontrol version of the trajectory to map in an optimal sense the ADSB version, you are not very far. It's the same actually. Okay, and you have more interestingly a bunch of trajectories for which the distance is not null. So there is benefit from working with ADSB data if you study shape, right? Because you need the extra information you have with ADSB data. You are also able to visualize things and to compute what I call the shortest path. So here it's one flight and the two versions. The one version is Eurocontrol and the second one is ADSB. And I want to bend and stretch the Eurocontrol trajectory to be as close as possible to the ADSB version, right? So I allow rescaling, rotation, translation, and reparameterization, okay? And when I do so, I can compute a so-called geodesic path of deformation, right? So this is the optimal way to bend and stretch, and then I can use this extra information in a clustering approach, for instance. Be very careful here. We are looking at square root velocity geodesics, right? So we are not bending original trajectories. There is a lot of work to rebuild geodesic in the other space. But at least you have one representation, and here you see that to go from one another, the main dimension on which you are going to play is the latitude, right? Be careful of the units here. Okay, we are living in something that is rescaled, translated, reparametrized, rotated, blah, blah, blah. Okay. And this is my application, hierarchical clustering. So what I do basically is that I use this geodesic distance as for creating my usual distance matrix, right, in clustering, and then I perform the clustering. What I noticed is that there are two main shapes here. There are trajectories that land from a given direction, and another bunch of trajectories that are landing the other way. Thanks to the geodesic distance, I captured the shape, the very shape of trajectories, and it's very efficient to cluster trajectory based on shape. And here, depending on the wind, of course, you are going to be in one case or another. So I tried to introduce rather complicated notion from geometry and namely a geodesic distance, but it helps, I think, to quantify correctly and to clarify the empirical assessment that flown trajectory may be far away from the flight plan. There are many, many ways to extend this work, I think, because it can be used in clustering problems, but also if you want to do some pattern identification in the TMA based on shape, helicopter flight characterization based on shape, go around study, and historically speaking, you have to know that the square root velocity function was used to classify protein shapes. So it's like same thing as go around for us, right? Of course, I'd like to emphasize that some performance comparison should be made with existing distances for clustering problems to know that is it the best option to cluster shapes, right? Also, my work focused on a sample of flights that is not representative of all flights in Europe, and I think we can find interesting patterns extending the database. And finally, my ADSB cleaning process was a bit fast to to be completely honest with you. I did some cleaning based on quantile or filters, uh, and it can be, of course, refined in future works. But I hope this brings back a bit of what we do in statistics and how you can use this in practice to solve operational problems. Thanks.